What if the strangest part of a black hole isn't a thing at all, but a direction you're no longer allowed to choose? Cross a certain line, and forward stops meaning space and starts meaning time. The center ahead of you stops being a place you're moving toward and becomes a moment you can't avoid. The same way you can't avoid tomorrow. Fire every engine you have, turn as hard as you can. None of it helps because there's no direction left called away. That's the part most descriptions miss. A black hole doesn't cage you with walls, it cages you by rewriting what later means. To see how something manages that, start with what a black hole actually is, because the popular picture usually gets it wrong. It isn't a hole punched through space, and it isn't a ball of crushed debris glowing in the dark. It's a region where gravity has bent space-time so sharply that nothing, not light, not radio waves, not information, can climb back out. Stars fall in, planets fall in, and in principle every atom in your body could too. Yet from outside, all of it simply disappears, even while the mass and gravity stay detectable. The edge where that disappearance becomes permanent is called the event horizon. For a large enough black hole, nothing marks that edge. No wall, no flash, no warning sign. So an astronaut could drift straight across it and feel nothing unusual in the moment it happened. The horizon isn't a surface waiting to strike you. It's the point past which every outward path has already been erased. To understand how a path can just vanish, it helps to go back to where black holes come from in the first place. Every star spends its life balancing two forces, gravity pulling inward and the pressure of fusion pushing back out. When a massive star runs out of fuel, that balance breaks, and the core collapses under its own weight. Sometimes the wreckage settles into a neutron star, absurdly dense, but still holding a shape. If the core is heavy enough, though, nothing stops it. Not electron pressure, not neutron pressure, nothing physics has ever measured. And the collapse keeps going, packing more mass into less space with every passing second. Past a certain point, an event horizon snaps shut around it, and everything happening inside disappears from the universe's view for good. That's one way a black hole is born. Growing bigger works differently, as black holes spiral together and merge, or gas and stars spill in slowly over billions of years. At the center of most galaxies, one has usually been feeding long enough to reach millions, sometimes billions, of times the sun's mass, with a horizon that can stretch wider than our entire solar system. Size sounds like a simple matter of scale, but it actually decides whether you'd survive the fall at all. Get too close to a small black hole and you're torn apart long before you reach the horizon, but fall into a supermassive one and you could cross that same boundary alive without feeling much of anything. The difference comes down to tidal force, the gap between the pull on your feet and the pull on your head. Near a small black hole, that gap is brutal. Gravity shifting so fast over just a few meters that a body gets stretched long and squeezed thin. Physicists call the result spaghettification, a funny name for something that ends with bones and cells pulled apart. Around a supermassive black hole, gravity changes so gradually that the horizon can feel almost gentle as you cross it. Gentle, though, isn't the same as safe, because the same violent ending is just waiting a little further in. Meanwhile, someone watching from a safe distance would see the whole thing completely differently. As you near the horizon, the light leaving you has to fight harder to climb back out, losing energy on the way. Stretching redder, arriving dimmer, showing up later and later. Eventually, your image fades into nothing, too faint and delayed for any telescope to catch, looking like you've frozen at the edge forever. But that's an illusion of the light, not something actually happening to you. On your own clock, nothing freezes. Time keeps moving exactly as it always has, and you'd cross the horizon in an ordinary instant, with no signal telling the outside universe it had just lost you. So, if it's not a wall, and it's not a slowdown, what actually stops you from turning back? Light itself isn't moving any slower near a black hole. It always travels at the same speed to the space right around it. What's changed is the shape of that space. The geometry itself has bent until every route curves inward. Outside the horizon, some paths still lead away, even if it takes a powerful engine to follow them. But right at the horizon, the last outward path runs along the boundary itself, going nowhere. Cross that line, and even a beam of light aimed straight out gets dragged back toward the center. Nothing is literally flowing like water down a drain. That image just helps the intuition along. Space-time has simply curved so completely that every future you could have points the same way, inward. Escaping would mean stepping outside your own future, which is just another way of saying it would mean outrunning light itself. An engine can't fix that, because acceleration only changes which inward path you take, never whether you take one. It's like trying to dodge the next second by running east instead of west, when the direction was never the problem. This is where a black hole stops behaving like a place and starts behaving like a clock. Ask what's inside. 1. And it sounds like asking what's inside a locked box. But a box holds objects arranged in space at one instant, and a black hole's interior doesn't work that way. In the simplest models, the direction pointing toward the center behaves less like a place and more like time. The singularity isn't sitting somewhere you could choose to steer around. It's waiting in the future of everything that crosses the horizon, the way next Tuesday waits in yours. Turn sideways, spin around, do whatever you want. You might change where you arrive, never whether you do. Even hovering becomes impossible, because holding still requires a path that simply doesn't exist in there anymore. Outside the horizon, a strong enough engine can hold a ship at a fixed distance, fighting gravity to a draw. But the closer that ship gets, the harder the engine has to work, until right at the boundary, no amount of thrust would be enough. Past that line, standing still stops being difficult and becomes a logical impossibility. So what would you actually see and feel on the way down? It depends heavily on the black hole itself, how fast it spins, how much charge it carries, what's swirling around it. Real black holes almost always spin, and many are wrapped in disks of gas heated to blistering temperatures whose radiation alone could kill a traveler long before gravity became the real threat. Some of these environments launch jets of particles stretching thousands of light years into space. All of that violence, though, happens outside the horizon. The black hole itself can stay almost perfectly dark. Cross the boundary, and you could still watch light from the universe you left behind, still catching up with you and following you through the horizon, warped and stretched into unfamiliar shapes and colors. Nowhere in that view would you see a gateway swing open or a tunnel leading somewhere else. Locally, the fall might feel unremarkable at first, like drifting through ordinary empty space. But empty doesn't mean safe, because the tidal forces pulling at you never stop growing. Eventually, different parts of your body stop being able to follow the same path through space-time, and the larger structures give way first, while individual atoms hold together a little longer. Deep enough, even atomic nuclei stop surviving whatever space-time is doing to them, as everything you were made of keeps getting pulled toward one final destination. That destination, in classical physics, is the singularity, and it's less a place than a warning sign. Treated as an object, it sounds almost mystical. Treated honestly, it's where an equation simply stops working. The math predicts infinite density and infinite curvature there, and whenever physics produces an infinity like that, it's usually less an answer and more a confession that a theory has run out of road. General relativity handles gravity beautifully, for planets, stars, and the whole visible universe, while quantum mechanics handles the tiny scale just as well, atoms, particles, the strange rules governing them. Deep inside a black hole, both theories are supposed to matter at once, and nobody has figured out how to make them agree. Relativity treats spacetime as smooth and continuous, while quantum physics says nothing stays smooth at small enough scales. Slam those two pictures together at the center of a black hole, and neither one survives intact. Classical physics gives you a singularity. A fuller theory of gravity might replace it with something we haven't discovered yet. Maybe matter reaches some unimaginably dense but technically finite state. Or maybe spacetime turns grainy at the smallest scales and stops behaving like the smooth fabric Einstein imagined. Some ideas simply have the collapse halt before infinity is reached. Others describe matter bouncing into some different phase of spacetime. None of it has ever been tested, because the horizon hides the one laboratory where the answer lives. Spin makes the picture stranger still. A black hole with no rotation is described by a solution Carl Schwarzschild worked out in 1916 while serving on the front lines, months before he died. While a spinning black hole needed a different solution entirely, one Roy Kerr finally found in 1963, nearly half a century later. Instead of a single point, Kerr's math predicts a singularity shaped like a ring, with a second horizon tucked inside the first. Beyond that inner boundary, the equations seem to allow bizarre paths through space-time, passages some interpretations even connect to other universes. That's more or less where every wormhole scene in science fiction comes from, though real rotating black holes almost certainly don't deliver on that promise. Near the inner horizon, tiny disturbances get amplified enormously as incoming radiation piles up and gains extreme energy, an instability that likely destroys the clean, idealized passage the equations describe on paper. What actually replaces it is still an open problem in physics today. Rotation also carves out a strange region just outside the horizon called the ergosphere, where nothing can stay still relative to the rest of the universe, dragged along by the black hole's spin. Unlike the horizon, though, it isn't a one-way door. Objects can escape from it and even steal energy from the black hole on the way out. Cross the true horizon after that, and the one-way trip begins all over again. All of this leads to a deeper question than what happens to any single astronaut. What happens to the information carried by everything that ever falls in? Quantum mechanics is built on the idea that information can bend, scramble, hide, but never truly vanish. And a black hole looks, at first glance, like it breaks that rule completely. The problem got sharper once Stephen Hawking showed, in 1974, that black holes aren't perfectly permanent after all, leaking a faint stream of radiation through quantum effects near the horizon and slowly bleeding away their mass. Small black holes lose mass fast. Supermassive ones would take far longer than the current age of the universe to fade at all. Given enough time, though, a black hole could in theory evaporate completely, and if all that's left behind is featureless heat radiation, whatever information fell in seems erased for good. That's the black hole information paradox, and it's unsettled physicists for decades. One possible answer is that the information never really leaves, just escapes disguised in subtle patterns hidden inside the radiation. Another says it gets encoded on the horizon itself, like a recording pressed into the boundary rather than lost behind it. Recent theoretical work has actually strengthened the case that evaporation can preserve information after all, even without a full explanation yet. Chasing that answer has pushed some physicists toward an even bigger claim, that spacetime itself might not be fundamental and that space instead emerges from deeper quantum relationships, connections rather than geometry, as the true bedrock of reality. If that's right, a black hole's interior might be less a hidden volume and more information rearranged somewhere we haven't learned to read yet. Even the size of that interior turns out to be a strange question. A horizon has a clear, measurable area set by the black hole's mass and spin, but the volume inside depends on how you slice space-time into moments, and different slicings give wildly different answers. Under some of those definitions, an old black hole could hide an almost unimaginably large interior behind a modest-looking horizon, a mismatch that points towards something even bigger. Black hole entropy scales with the horizon's surface area, not the volume it encloses, and that single fact reshaped physics. It helped inspire the holographic principle, the idea that everything inside a region could be fully described by information written on its boundary, so that a three-dimensional world might have a complete description using only 2 dimensions. Black holes may be the clearest hint we have that reality actually works this way. Every object that falls in changes the horizon's mass, spin, and hidden microscopic state, like a ledger quietly updating itself. Yet from outside, a settled black hole reveals almost nothing about its history. Just mass, charge, and spin, nothing more. 2 black holes with completely different pasts, one fed on gas, the other on stars, could end up looking identical from the outside. Their history's not gone exactly, just encoded somewhere nobody yet knows how to read. So what's actually inside a black hole? The honest answer depends on which question you're asking. Matter is inside, in the sense that stars, gas, and entire worlds have crossed the boundary and never come back, and curved spacetime is inside too, reshaping every possible path until all of them point toward the same future. A singularity is inside, at least according to the classical math we have now, though some undiscovered quantum structure might be there instead, waiting for a better theory to describe it properly. And information is inside too, tangled up in ways nobody has fully worked out yet. What's definitely not inside is a quiet pile of debris sitting still and waiting to be found. Nothing that falls in stays arranged the way it started, because collapse and tidal forces reshape everything that crosses the line. No probe has ever crossed a horizon and sent data back, and, by definition, none ever will. Gravitational waves and telescope images can only tell us about the outside of a black hole, never the interior. For now, the true interior stays a place reached only by equations, never by instruments, and those equations carry us right to the edge of an answer before hitting an infinity and stopping. The mystery isn't just that we can't see inside a black hole, it's that our deepest theories don't yet agree on what seeing inside would even mean. Until one of them wins, a black hole stays what it's always been, the point where the universe stops explaining itself and starts asking us to guess.